Welcome to this complete physical sciences lesson, brought to you by Elucidate Scratchpad. Today we work through PS1b, Newton's laws and connected objects. In this lesson you will state Newton's first, second and third laws in exact words, declare and apply a sign convention for F net equals ma, write the sign equation for a single object, separate the equations for each object in a two-body system, use the system method to find the common acceleration and the tension, add the downslope component and friction on an incline, and then transfer the method independently. Each question is answered and explained line by line, exactly as you would present your work in a memorandum. Follow along, and try each step before you read the answer. Question 1.1. A trolley moves at constant velocity while several forces act. Which law applies? Constant velocity means there is no change in motion, which means zero resultant force. That is Newton's first law. Newton's first law covers both rest and uniform motion, so the answer is Newton 1. Question 1.2. A non-zero resultant force causes an object to accelerate. This is the signature condition of Newton's second law. A non-zero net force produces acceleration in the direction of the force. So the answer is Newton 2. Question 1.3. The sled pulls backward on the snowmobile, while the snowmobile pulls it forward. These two forces act on two different bodies, and that is an action-reaction pair. Newton's third law says the forces are equal in magnitude and opposite in direction, but they never cancel on the same object. The answer is Newton 3. Before we write your answer, hold this slide in mind. Newton's second law carries for examination phrases, and everyone is a mark. Non-zero resultant force is the cause. The object accelerates in the direction of that force. Acceleration is directly proportional to the resultant force, and inversely proportional to the mass. In an exam, if you miss any one of these underlined phrases, you lose a mark. So when you complete the wording, protect all four. Question 1.4. Complete the wording of Newton's second law. Acceleration is directly proportional to the resultant force, and inversely proportional to the mass. Those are the four mark-carrying phrases: the non-zero resultant force, accelerating in the force direction, directly proportional to the force, and inversely proportional to the mass. You have completed stage 1. The laws are matched, and Newton's second law wording is complete. This whole stage is about one idea: F net equals ma is a signed equation. Before you calculate, you declare a positive direction, then you project every force onto that axis. A force pointing with the positive axis is positive, a force pointing against it is negative. Arrow direction, not the name of the force, decides the sign. Right positive and left positive are both accepted, as long as you use your choice consistently. Question 2.1. Choose the positive horizontal direction. Right positive is the natural choice here, because the snowmobile accelerates to the right. Both right positive and left positive are accepted, but you must declare your choice and then use it consistently. Question 2.2. With right positive, how does the applied engine force enter? The applied force arrow points to the right, along the positive axis, so it enters as positive. Question 2.3. With right positive, how does friction enter? Friction acts to the left, against the positive axis, so it enters as negative. Question 2.4. The vertical resultant force while the snowmobile accelerates horizontally. There is no vertical acceleration, so the vertical forces balance and the vertical resultant is 0. You have completed stage 2. The sign convention is declared, and every force enters with the correct sign. This is the heart of the two-body method. Write one signed equation for each object with right positive. For the snowmobile, the engine force drives forward, while tension and friction pull back, so F minus T minus F1 equals M1A. For the sled, only tension pulls it forward and friction resists, so T minus F2 equals M2A. Now add the two equations. The tension terms appear with equal magnitude and opposite signs, so they cancel. That is why tension disappears only inside the combined system equation. It is an internal force of the two-body system. Question 3.1. The snowmobile, mass 258 kilograms. With right positive, list the horizontal forces. The engine force drives to the right, so it is positive. Tension pulls the snowmobile backward, and friction is to the left, so both are negative. That gives F minus T minus F1 equals M1A. Question 3.2. The sled, mass 50 kilograms. Look only at the forces on the sled. Tension pulls the sled forward, so it is positive. Friction resists to the left, so it is negative. The equation is T minus F2 equals M2A. Question 3.3. Explain in your own words why tension disappears from the combined system equation. Tension is an internal force of the combined snowmobile and sled system. The two tension forces have equal magnitude and opposite signs, so when you add the two object equations, they cancel. You have completed stage 3. Each object has its own signed equation, and the internal tension cancels in the system equation. Question 4.1. Combine the masses. The total mass of the two-body system is M1 plus M2, 258 plus 50, which is 308 kilograms. Question 4.2. Total external horizontal friction. Add the two friction forces, 91.64 plus 87.59, which gives 179.23 newtons. Question 4.3. The common acceleration. Treat the two bodies as one system, with right positive. Engine force minus both friction forces equals total mass times acceleration. Substitute, 1381.64 minus 179.23 equals 308 times A. This gives an acceleration of 3.90 meters per second squared to the right. Question 4.4. The tension. Return to the sled equation, T minus F2 equals M2A, substitute 87.59 for friction and 50 times 3.90 for the mass acceleration product. Isolate T, and you get 282.8 newtons. Keep the unrounded acceleration until this final step for accuracy. Question 4.5. Reasonableness check. Compare with the single snowmobile, which accelerated at 5 meters per second squared. Now the engine pulls more mass and overcomes more friction, so the attached system acceleration is less than 5 meters per second squared. That matches the 3.9 we found, so the answer is reasonable. You have completed stage 4. The common acceleration is 3.9 meters per second squared, and the tension is 282.8 newtons. An incline changes the picture. Put one axis parallel to the plane and one perpendicular to it. You rotate the axis, not gravity. With up the plane positive, the applied force is positive, while both friction and the component of weight down the plane are negative. So the sine sum is F minus Fk minus mg sine theta, all equal to ma. Do not forget mg sine theta, it is the part of the weight that acts along the slope, and it must be included. Question 5.1. With up the plane positive, choose the correct parallel equation. The applied force acts up the plane, so it is positive. Kinetic friction and the component of weight down the plane act against it, so they are negative. The correct equation is F minus Fk minus mg sine theta equals ma. Question 5.2. Calculate the normal force. There is no acceleration perpendicular to the plane, so the normal force balances the perpendicular component of weight. Fn equals mg cosine theta. Substitute 258 times 9.8 times the cosine of 17.1 degrees, which gives 2416.6 newtons. Question 5.3. Calculate the kinetic friction. Kinetic friction is the coefficient times the normal force, mu k times Fn. Take 0.036 times 2416.6, which gives 87 newtons. Question 5.4. Why is mg sine theta included? It is the component of the weight down the plane. On a slope, only that parallel part of the weight acts along the axis of motion, so it must be added to friction in the sine sum. You have completed stage 5. The normal force is 2416.6 newtons, and the kinetic friction is 87 newtons. Question 6.1. A car moves at constant velocity on a level road. Constant velocity means zero acceleration, and zero acceleration means the resultant force is zero. The answer is 0. Question 6.2. At constant resultant force, the mass of an object doubles. Since acceleration is F net over m, doubling the mass halves the acceleration. Question 6.3. Which statement identifies a Newton 3 pair? An action-reaction pair is the same interaction acting on two different bodies. The correct answer is, the snowmobile pulls the sled, and the sled pulls the snowmobile. Question 6.4. Explain in two linked statements. The inextensible string constrains both objects to move together, so their accelerations are equal in magnitude. And tension is an internal force of the two-body system, so it cancels only when you write the combined system equation. You have completed stage 6. You have connected Newton's laws to the two-body method through independent transfer. That completes the PS1B lesson on Newton's laws and connected objects. You have seen each question answered and explained line by line in the memorandum style, and you can see exactly how a verified free body diagram becomes a sine Newton law equation. Practice this method again to build fluency, complete the interactive Scratchpad, and then attempt the examination level exit ticket. When you are ready, move on to the next lesson in the course.